The second opportunity. So I will completely switch gears now, so you can essentially forget the last talk. You should remember it a little bit, but we'll now come to geometry. So we start with x. So x will be this will be smooth n-dimensional complex variety, complex projective variety. So you can think about this also as a compact manifold that is embedded in some projective space. And we'll say it has a fibration, so pi to a fibration to v. So this will be n-1 dimensional. And same smooth n-dimensional complex projective variety, and pi will be elliptic fibration. So by this I mean it's in algebraic geometry words, it's a flat so it's a flat morphism whose fibers are one-dimensional reduced curves of arithmetic genus 1. Okay, so whatever this means, that means that so the fibers of what can be the fibers of this pi. So these are just reduced curves of arithmetic genus 1. And so what are examples of the generic fiber? Really a smooth elliptic curve here. So this is elliptic curve. And then you can have, I mean, in the base, this was already explained, you have the discriminant. This is some divisor. Along the discriminant, your elliptic curve, your elliptic fiber can degenerate to some singular ones. So for example, you can have the nodal elliptic curve here. Okay, so where you degenerate one of the periods, so this is potentially a generic point of your discriminant, so generic point of the discriminant, defined with this. This is a nodal cubic. You can also look at a cuspidal cubic, so cuspidal cubic, I don't know how to draw this. So so let me draw the algebraic picture. So this is a cuspidal cubic. So locally, this looks like equation y squared equals x cubed. But you can also have this kind of I2, I3, I4 Kodaira fibers. So you can also have things like so the IN. Well, that's not IN. So for example, IN fibers, and then also whatever the EN. Yes, you can have more complicated. Maybe here I should maybe really draw this as a zero. So really there's a lot that can happen. A further assumption we make, and that's an important assumption, we assume that this section pi has a section. Okay, so there's so I goes from the base to x, such that if you compose it with so pi composed with I, it's just the identity. Okay, so we go. And so in particular, this x then has a Weierstrass model, and we can describe it now. And so we want to do Gromov-Witten theory. And I want to define this Gromov-Witten potential or generating series. Let me just write generating. Here I want to define it relative to the base. Okay, so what's really remarkable about what I'm going to say is that it works for arbitrary elliptic fibrations satisfying this condition. So E could be 100-dimensional and X could be 101-dimensional. It still works. So this could be Calabian, B could be Calabian, could be Fano, could be anything. But what's important is that the fibers are elliptic curves. This is where you see the Calabian is coming in. The mirror symmetry, the modularity comes from the fibers and the elliptic fibers. That's kind of the thing you have to keep in mind. So really you should focus on setting up everything relatively in a nice way. Okay, so we start with a genus. And we start with a curve plus beta in the base. And then I want to also, out of our curves that we consider in our X, will pass through some cycles here. Okay, so pass through some cycles here on the homology. And then I want to define the potential Fg beta with some gamma 1. These are linear space because I will modify this slightly later on. But for now, just ignore the space. So, and so this should be a generating series of Gromov-Witten invariants with respect to curve classes that map down to this beta. So that in some sense, two things you could do. You could take beta and you add up multiples of the fiber classes. And this is what people usually do. The problem with this is you kind of don't see part of your cohomology upstairs. It can be, for example, you don't see this IN fibers there. So of course you could introduce a variable for each of the IN fibers and so on. But that comes out to be kind of ad hoc in some sense. So you have to kind of, for each case, you have to kind of write down the basis and so on. So the more natural thing to do is to really sum over all the curve classes upstairs that push down to the given curve class beta. The pi is a proper morphism, so you can just push forward homology classes. So we'll introduce a variable q here. I will come to that in a second, and introduce a variable p here. And then here we'll have our Gromov-Witten invariants, gamma 1, gamma n, of our space X in our given genus and our given vector. That will be the general format. This will be a series now. If I can define it correctly. Will be a series in, and we'll have odd powers, half integer powers of p, and then this p plus minus 1, and we also will have some denominators in our g. So I have to first tell you what is this Gromov-Witten bracket. So,
but what do you mean by summing over all beta tilde, or do you choose some list?
No, I choose. This is what is fixed.
Yes, you choose, but beta tilde.
Yeah, I sum over all beta tilde that I push forward to this, and I put here a variable, and I will weight this variable with something related to, such that if you fix this exponents of q and p, you only get a finite sum of this beta tilde. Okay, so this will come, but first I have to, of course, tell you what comes here. So this is what I will do next. So first, I can first explain what is this part, and then explain the variable part. Okay, so let me first quickly say what are the Gromov-Witten invariants. And this is in some sense impossible because there's a lot of technicalities that go into it. Naively, what to think about naively is this is a count of genus of maps, of stable maps. From the curve C to your target variety C, where C is of genus G. The push forward of this curve class C is better. And then this map is incident to cycles Poincare dual to this gamma 1 to gamma n. So F of C is incident, and with cycles gamma I such that the class of this gamma I is Poincare dual to this gamma. So what does it mean, incident? It's like me. Okay, I mean, trying to say the curve is incident to a point if the point lies on the curve. So I mean, you have some conditions here, some cycles. You have the X, and you have some points, maybe a subspace here, gamma 2, say gamma 3, gamma 1, gamma 2, and you count the number of curves which are algebraic curves which are meeting them in a given G. And so, of course, to do this rigorously, what you really do is you integrate over a certain moduli space, which is the moduli space of stable maps, which parameterizes this data to your target variety X in this class beta. You also parameterize this n markings. So you parameterize the data of this map together with n markings. Then you have to think about what happens if your curve C degenerates, which can happen. So you have to think about this as a stable map. So the C will really be a nodal curve and so on. So you have to think about this and define this as a model space. This will be then a proper Manford stack. And it has an actual class, the cyclic class, this virtual fundamental class. And then you just integrate over this class.
So sorry, this quantity doesn't depend on the choice of representative of these gammas.
Yeah, it doesn't depend. It just this is just for to get some intuitive feeling. So it's really in the section number on this moduli space between this cohomology class. And so this means, of course, often the enumerative meaning of these numbers are not clear. I mean, what do they count? Who knows? It's just some invariance that you associate to your space X. And they are nice in the sense that they don't depend on X when you deform X. So this is why we like the invariant. They just depend on the information type of it. So yeah, this setting this up really requires a lot of work, but you should just think about this as some moduli space like the Grotzianian. We intersect some nice cohomology classes coming from the geometry on this moduli space. Producing
when you say deformation of X, you mean any deformation or scalar or complex structure or
as a complex projective.
Okay. Complex structure deformation.
Yes. If you have a complex structure deformation, this number stays the same. So for example, if the elliptic curve doesn't matter which elliptic curve you take.
Yeah.
And so.
So do Q and P have some powers associated to them, or
I mean, I come to that now.
okay. That's a blank.
I mean, I had the choice what to do first. If I do this one first, then nobody cares about this one. So now I explain this one. So I explain this one. Now I will explain the powers.
From this algebraic point of view, how do you see the dependence on the symplectic structure of the definition?
I mean, if you have a complex projective variety,
is it easily
it's a Fubini study method.
Okay.
Something restricted to get a kind of elements. Yeah, so yeah, of course, you can just work in the world of symplectic geometry and have it in a more complicated situation. In algebraic geometry, it's much nicer to compute. So this is why I always stay in algebraic geometry. Okay, so I have to. Okay, I remove this reference. And
still, how do you see the dependence on the polarization from this definition? So,
the polarization of your variety.
Yeah.
You mean of the ample class or something?
Yeah, is there a way of seeing that?
Yeah, we'll come to. I mean, this comes from the powers.
Oh, okay.
We're trying to get there. So pi is elliptic fibration. This is smooth n dimensional. So, and you don't need this. So, but what's important here is to think to remember that there's a section. So I keep the section. And so the key here, the definition is to define the divisor, which is essentially the divisor of the section. So the B is n minus one dimensional image is a divisor. So you want to define, look at the section, but that's not good enough. So you have to correct it by something. And let me just be correct. Not making mistakes. So we have to correct it by a certain factor, which is exactly the pullback of the C1 of the normal bundle of the section inside it. So just to explain this, so you have your B, so you have the X, and your B sits inside of this. So this is your B. And then there's a normal bundle here. This thing, which is the normal bundle to B inside X. If you have a trivial elliptic fibration, the normal bundle is trivial, then you don't care about this factor. But in most cases, it's non-trivial, so you have some kind of twisted.
So this is like if it were a square root of the canonical bundle of B, it would be like the first sentence of that.
Yeah, I mean, if say it again.
So is there a relationship between this correction and the first class of a square root of the canonical bundle
Of the base?
Yeah.
Yeah, so let me make this as a mark. If X is Calabi-Yau, right, this means that omega X is trivial. And if you restrict the tangent bundle of the X to B, this has also trivial determinant, but then there's a fibration here. Normal bundle B over X. So if you take the determinant of this sequence here, this tells you that the determinant of this one, which is just a restriction of this one, this is just trivial, is isomorphic to the determinant of TB. Cancel the normal one. And this is, of course, the dual of the canonical bundle. This is so this tells you that the omega B is just isomorphic to the normal. Okay, so what we do here is we just put W times this beta T. And already, if you now you know the P, now it's a well-defined thing. So once you fix the fiber degree, you know that the section plus multiples of the fiber is the ample class, and then there are just finally many of this beta tilde which project down to the end. So in some sense, this is already enough to make the sum fiber finite for each two coefficient. But we can do more. We can add another variable here related to. I forgot the name, how you called it, but to also keep track of homology, which is does not meet B the section, but maps down to 0 here. For example, this curves sitting inside this IN fibers. So we can keep also track of them in this. And so the way to do this is to define an operator, define a weight operator. I call them also weight. And this is just given by the commutation between coupling with this W and the pushing forward by the fibration and then pulling down. Okay, so if you think about this, the weight of gamma does two things. So you pull back, you push forward gamma and pull it back again and couple it with W, and then you subtract it if you do it the other way. And so this is diagonalizable. So this acts on a homology on X and it's diagonalizable. With eigenspaces, eigenvalues 1, 0, and -1. So then we write it as 1, -1, and 1. And what are the eigenspaces? So the eigenspace to eigenvalue 1, eigenspace to eigenvalue 1 is stuff that if you project down and push it and pull it back and couple with W, it stays the same. So I'm just saying this is W times the pullback. Okay, so you can convince yourself easily of this. So if you have something which is W times the pullback, okay, so this part is maybe not so, you have to make a calculation, but maybe this one is easier first. So this one is just a pullback of the homology. Okay, so if you have an element here in this guy here, the pullback of homology of B, if you apply this operator, if this part here, the push forward of a pullback is just 0, and so here if you have a pullback, you couple with this W, that means essentially you restrict it to the section and then push it forward, you get the same guy back. So then you get a -1. And for this one here, essentially the first term is clear, and in the second one you get something like W square. Essentially this W is chosen in a way that it squares essentially it's essentially 0. So is that correct? Or at least it's pulled back from the base. I think this is the better way. Okay, so and so then there's the last piece, which is the eigenspace to, and this I call it H curve of B, eigenspace of 0. This is what I call H curve. And the last thing is what we do is we fix the D is H2 X. And the P value we take is just E times this.
One question, are the eigenvalues 1 minus 1, 1 or 1 minus 1, 0?
I'm sorry. Yeah. So I tried to match this line here. So it should be 1 minus 1 and then here. Sorry.
So does this depends on this class B or does this depends on the choice of class D?
This guy here.
Yeah.
It depends. Of course, what you can do is you can take the basis of this and then put this is R dimension. You can take R of these devices, D1 to dr, introduce R variables here, and then you get this higher index Jacobi forms or partial forms. And you can do all of this, and this is the way we did it in the paper. But just do it like this here to match. To make it simpler and also to match but I think you also have the higher lattice Jacobi form.
So, sorry, if I understand correctly, this is supposed to capture this gauge degrees of freedom.
Yes. So D would be the Shioda map.
Okay, yeah, I was about to ask. So, what is the physical meaning? Okay, the
D is the Shioda.
Okay.
So yeah, actually. Okay.
Is D somehow capturing the class of the fibers?
Yeah, so intuitively, let me just draw a picture here. So a curve here will, you have the fibers here, the smooth fibers. We can call the fiber class F, but then you also have this IN fibers. And the W here, the W is essentially the section. So if you have a beta tilde times W is equal to some number D, it tells you your curve that you're studying hits this section D times. So it just keeps track of the number of fibers. And then this D here keeps track of, for example, this curve here, one of these curves. So for example, this one. Take this, whatever is gamma, and then D could be, for example, some gamma mu or whatever. Something that just is 1 on this fibers, but on 0 everywhere. Of course, you could choose a basis and do all of this. This is kind of the most natural way. That is not, that doesn't, it sets this up more naturally. And so let me state the conjecture conjecture.
If there are no EM fibers, then the dependence on P is strict.
Yeah, so if you, for example, if you, it could be that this H prop is 0. The H prop of X is 0, this could happen. Then you can take D to be 0. It doesn't matter. So then you just take P to the 0, it's just 1. It doesn't matter. So you can take in this thing, if you don't like this P, you can just take D to be 0. And it's valid. And so the conjecture is this FG beta. And let's say we have this gamma 1, gamma n. This is a quasi-topology. And so, yeah, up to this factor of data. So we have the weight. I don't specify the weight yet. I will specify it in a second. And then here we have an exponent which is minus 1/2 of C1 of the normal bundle of D in X times this plus Z. In the M, the index is just given by minus 1/2 times integrating the pullback of this class beta times the square of this numerator. So this is really now an integral number. So this is really that. And C has no character. So this is really honest quasi-Jacobi form in the way I defined it. So there's no problem. And so the weight of this is also very interesting. So the weight of this whole thing here the weight is just 2g minus 2 plus the number of markings plus the weight of this class. And the weight of this classes are exactly the eigenvalues of the classes under this operator, the weight operator. So here the definition, so if you assume your gamma 1 to gamma n are eigenvectors of our weight operator, then by definition they are just the eigenvalue. So weight of gamma I is equal to the little weight. So this is large weight of gamma I times gamma. If you have a single simple operator, it defines the grading of your vectors.
So the calculation in Timo's lecture, I guess this is a question for Timo. It depends on this conjecture. Your check of the weak probability conjecture does depend on this conjecture. I mean, you take this for granted.
We essentially took this for granted. We checked it, and we get a physics derivation for the case of fourfolds. But you are of course much more general.
I mean, yeah,
and the results depend for the grading conjecture depend on this being true.
Yes, right.
But this is, I mean, this is okay for mathematicians. We are unsatisfied, but physicists. And also there's a derivation in physics, as Timo said, for many geometries, and also many. There's many proven cases of this also. So we have some ideas how to prove this in general, but okay, so let me state the holomorphic anomaly equation. So what's that? How much time do I have? 15 minutes. Okay, so I want to state the holomorphic anomaly equation. And
a bit more.
Can you say just one word about what do you know about this conjecture? In which cases is satisfied?
Oh yeah, that's it. Okay, I can make this. So where is it known? So here, and that's many people. So let's say if you have elliptic curve, that's the first case. And this is essentially Okunko from back in the 20 years ago. This is known. You can also look at some sort of orbifolds of elliptic curve. So elliptic curves modulo a finite quotient. And this is you can view as some elliptic fibration, which is also nice. And you can look at the rational elliptic surface, which is what's called a half K3 or something. Rational.
So by elliptic curve, you mean X is an elliptic curve? You mean X is an elliptic
X is
curve?
elliptic curve.
Okay,
And
so
B is a
B is point.
Yeah, B is the point. I mean, it's a stupid elliptic fibration, but it's the first example to study. It's and then you have this one, the same, B is a point. Then you have rational elliptic surface. Surface. Which is you take two cubic elliptic curves in Q2, you look at the intersection points and blow them up, and then you get the vibration. So rational surface with the vibration over. There's also the elliptic K3. K3, where most of this is known. You have to modify this conjecture. It's okay. And then if you have products, so if X is a product is also known.
Okay, so X does not have to be a Calabi-Yau manifold.
No.
Okay. Biased.
It could be, it could be Pn times elliptic.
Okay.
Yeah, that's kind of a cool story. It's just the fibers is what's matters.
So for 3 folds or 4 folds?
Yeah, I don't think that, for 3 folds. Yeah, of course, for example, if you degenerate, for example, you can also do it for the shrink Calabi-Yau 3 fold. So if we have shrink Calabi-Yau 3 fold, this is also a case where it's known, because it just reduces to the case of this rational elliptic surface. So that's mathematically proven.
Does the Calabi-Yau condition as such make your life easier with this conjecture?
No. So the Calabi-Yau condition doesn't have to prove it yet. I mean, in some sense, it helps you a little bit because for example, Calabi-Yau 3 fold, all this gamma 1 to gamma n, you don't need to specify them. You just get But in general, no, it doesn't help. Sometimes the less Calabi-Yau you are, the easier it becomes. Sometimes Calabi-Yau is the hardest.
For the homogeneous spaces, Riemannians.
Yeah, so then you don't have elliptic fibration. Of course, you can take the base to be. Yeah, but it's not clear. So, for example, elliptic vibration over P2, there's no mathematical proof. I think there's local cases, but yeah. So you don't really, also for elliptic Calabi-Yau 3 folds, there are many cases, for example, elliptic Calabi-Yau 3 fold over P2, elliptic vibration over P2. This was calculated in physics, for example, by Albert Schrem in many cases to high degree, and the exact same matches this conjecture. So I think the evidence is pretty convincing. Okay, so I want to state the holomorphic dynamic question now in the last 15 minutes, 15 minutes. And so I said that we need to modify this a little bit for this holomorphic dynamic equation. So if you just want to take it, so now the holomorphic dynamic equation tells you the dependence of this FG beta on this A and on this G2. But to write down the dependence, I will leave this word of this functions defined in this way, but have to slightly generalize it. Okay, so I will have to define Gromov-Witten descendant invariance. So I will go back to this point and generalize this a little bit. So I use this. Let me use a green color. So can you read this green?
Yes, but
Okay, so I use orange. Descendant. So orange is okay, so in some sense, this descendant invariance is about not keeping track only of incidence, but also of tangency at the cycles in an intuitive way. What's really happening is that you instead of integrating over this guys, you integrate over additional classes that come up to psi 1 to the kn and psi n to the kn. Well, actually, I forgot the most important thing in this whole business. Okay, so I forgot something. So, okay, I erased this. Okay, so let's forget about this thing. I forgot something. So, find the weight operator. Yeah, okay. Okay, so let me redefine everything. Okay, so what was our definition? Okay, so of this Gromov-Witten potential, we fixed our genus, we fixed our curve class H2, and then we fixed our cohomology class. And then the main thing is we have to make an assumption, assume either that 2g minus 2 plus n is positive, or that the curve class is non-zero. Otherwise, I will not. This function is not defined. Okay, so otherwise. FP beta is not defined. And for the experts, this is, or whatever. The reason for this is if you take beta to be 0, then you have to also allow the term where beta tilde is to be 0. And if you take beta tilde to be 0, then what is the moduli space that you think about? If this is 0, the moduli space is just mgn times your target x. But mgn is only defined if you have this condition. Okay, so it seems kind of silly. I mean, it just seems like a footnote or something, asterisk or something in it. But otherwise, this conjecture is wrong. Okay, so otherwise, there's no way to make sense of it. So this is only true in this if you have this assumption. Otherwise, it's not. I mean, otherwise, this is not defined. Okay, so. And why do I remember this when I put this psi here? And this is also the point here. So this is something also that you can ignore, but as you say, if you have this assumption here, this pi map induces you a map here to the base, to the moduli space, a stable map to the base. So here we have actually the beta tilde. And you have the beta tilde and you work with this assumption, you get an induced map here to the base. And what of psi 1 is the pullback of the first term class of the cotangent line bundle on this space Li. So Li here is the Li at the map here is the cotangent bundle. So it's a very subtle difference between the usual definition of the psi class and this definition of the psi class, but this is what we need.
What's the difference in the usual and this definition? Just repeat that.
So usually you just take the first term class of the cotangent line bundle up here.
Okay.
But here you take the first term class, you take the cotangent line bundle here, and then take the first term class and pull it back. And the difference is essentially just the boundary of the moduli space. It's not relevant for this talk in some sense, but I want to be honest somehow, and it's not lie. So maybe somebody. So it's a technical detail that you have to take the right psi class. Okay, and so then, so you have this extra data of this integers here in here, and then you get also the extra data of this generation. And of course, if k1 to kn is 0, you just get what you had before. So if you don't want to think about this, then don't think about it. Just take all the k1 to kn to be 0. And it's okay. Okay, so now let's write down the holomorphic anomaly equation. So now I have to kill something. Are there any questions? Okay, so now let me just write down the equation.
Well, for this tangential, so if there is a physics proof, are you going to discuss the physics proof or? No. But so could you say some words? What's the physics intuition? Why this conjecture should be true? If there is any.
Maybe I'll say tomorrow.
Okay.
I don't want to.
Okay.
So the same conjecture is true if you put a tau k1 here and tau kn. So and also the same data. Okay, so now let me
Sorry,
just.
what I miss what are the tau k1, tau kn. The tau k1, tau kn are.
Yeah, the one where you include the psi classes in the integral. And you get a different Gromov-Witten brackets, you get this tau k1 bracket. And then the generating series is just about the same. It just has a small algorithm. So the conjecture. And essentially there are two ones you need to specify. The most important one is the G2 holomorphic anomaly equation. And let me just give it to you, and then K1 of gamma 1. In some sense, I could give you a whole talk about this, the form of this equation, but I mean, that's maybe say too much, but you can say a lot about the form of this equation. I will just give it to you, and then. So the first term just drops the genus by 1. But you have to pay a price, and you have to include an extra homology class here. And the one you include is just the diagonal of the base B. Okay, so you take the diagonal B, the homology class in the base is the class of the diagonal in B cross B. And you can just put it back to the homology of X cross X by the projection map. So pi here I also write for the projection map too. And then there's the sum. And then there's the sum also over the splitting of the markings. So you split the curve classes, you split the genera, you split the markings. And so here you have FG1 beta 1. And here you have FG2 beta 2. And so the markings which are labeled A will go into this pocket. And here, let me just write it as here tau of gamma A, Ka. And this is just the product of the I inside A of tau Ki, gamma I. And then here is the tau Kb of gamma B. And then you have to again insert another one, which is essentially the diagonal, but you put it here and here. This, I mean, the first factor you put here, and the second factor you put here. And then there's the third part, which is that one. And this is why we need this operator. The sum over the markings, the genus stays the same, the beta stays the same. And all of the insertion stays the same, except for the I. The I, you just replace the tau Ki by tau Ki plus 1, so increase 1. And then the gamma I, you apply the following operator. And then the rest is the same.
Can you say by words what is the last entry of the first summer? In the first summer, yeah, what is that?
Yeah, so So if you take the unit decomposition of the diagonal, and by this I mean this is just the summation over I of tau 0 of delta I, tau 0 of delta I duals. So I'm just, listen, if you have tau A, tau B of gamma 1 tensor of gamma 2, this is just tau A of gamma 1, tau B of. And so, I'm saying, why is this the most interesting one? Now I can come back to my last talk, the end of the last talk, which is the Lie algebra relations in the ring of quasi-Jacobi forms. And one of the Lie algebra relations was that d over dA is the d over dg2 times the dz. And here's maybe minus 2. And so you can think about this dz also geometrically. You can re-express this as inserting here an extra insertion. And so once you know this equation here, it tells you also the corresponding equation d over dA. So this is really the kind of the meat or whatever that. Yeah, the most important thing.
Question. So the usual context in which I've seen the holomorphic anomaly equation is that okay, you consider the dependence on the Kähler parameter of x, and then you have a anti-holomorphic parameter. You have a holomorphic parameter and you have an anti-holomorphic parameter, and this is basically you. This basically gives you the dependence on the anti-holomorphic parameter.
Yes.
In terms of lower general ones, and how do you retrieve that usual notion of the holomorphic anomaly equation from this more?
Yeah, so this we had this discussion that the G2 derivative essentially comes from this d over d nu derivative from before, and the nu is our non-holomorphic parameter. Your question is, what does it make? Is there some sort of completion of this FG beta that makes sense geometrically?
Yeah. Can you put this into some series, like, because now you're isolating every beta here, right? Rather than considering all the betas at once.
No, this is not what you want to do. So so you can ask. So somehow this one was for a function for quasi-Jacobi from F, and then this one acted on the F hat, which is the non-holomorphic completion.
No, I mean that. So okay, like if you take the sum of all the Gromov-Witten invariants over all the degrees, and basically that's it. I mean the generating function over the degrees involves the Kähler parameter.
Yes.
Right. The expansion parameter over the degrees. That's the Kähler parameter, right?
Yes.
And there is. And because of some boundary phenomena of the on the moduli space, you have to also include some dependence on an anti-holomorphic parameter.
Mm.
But in this setting, you're not really changing a Okay, no, okay, fine. I guess it comes out to the
you sum here.
Okay, right.
Of course, you can ask, what does this nu here mean? What does the non-holomorphic extension mean? But I have no geometric answer for that. This is beyond some.
But where do in what? How do you get back the holomorphic anomaly equation for usual Gromov-Witten generating functions instead of this more refined version which involves Q and P?
So you can just have P equals to 1.
Okay.
If you set P equals to 1, you just get quasi-modular forms. You get just the usual one. So I can mention that in the last my last comment here.
Okay.
I'm kind of out of time. Let me make one more remark about this formula, because this is what I like about this, because they look like 3 different terms, but essentially it's the same term. And what I mean by this is, for example, if you think about this operator here. So if you think about this operator is an element in the endomorphism of the cohomology of X. But the isomorphism of the cohomology of X is just the same as the isomorphic to the cohomology of X cross X. And just by concrete duality. And under this isomorphism, this operator is exactly the diagonal. And so, in some sense, it's all the same formula. You can make that. So, and for these cases that I wrote down here, both of these conjectures are unknown. Okay, so I'm out of time. So let me just say that if X is Calabi freefall, this recovers the usual holomorphic nomenclature by, so let me just write DCOV, and then there's also work of Clem and other people. So I don't know the literature so well, so let me just write it like this, and if somebody wants to correct me, then and here, because of here the beta, you don't need any cohomology insertion, so you only have this FT beta, and then here you have empty set, so you just get a single series that you have here, and then you from this one you do a calculation. It's just a direct calculation, and it's in the notes. So if you're interested to, it's there, and you get the standard form. And then if X is Calabi fourfold, you also get what is expected. Expected. So I learned this. I mean, this and it matches what was known in the paper. Let me just mention this. What is expected slash matches this work of I think it should be here, maybe. Ah, there you are. And then Clement Schimmer. Let me get it correctly, Schimmer. And then I think it also matches what Timo is doing, and Weigand and collaborators. So maybe I stop here because I'm already.
Thanks a lot.
Yeah, I see the explicit equations in the notes. So
Can you write them again? Or
the what?
is the same? Is the same
Yeah,
webpage that you were at the beginning?
Yes. And it's also on my webpage linked. So I put a link now on my webpage. And I will add add a little bit of more stuff in the next week. So, yeah, you see explicit formulas for the calculation in there, and also parts of the calculation.
By the way, so when Q and P are both 1, does the term with the derivative of G, with ddg2, that term drop out?
No, you cannot set Q equals to 1 because that's you have infinite. So if you fix a Q coefficient, then you have the whole polynomial in P. So just find in many terms in P.
Okay.
But you always have infinite many terms in Q. It's like so if you have something like a delta of Q, and you cannot set Q equals to 1. It doesn't exist. Okay. So you cannot get rid of the Q, only get rid of the P.
What was the mathematical reasoning for conjecturing it? So did you generalize the known examples, or why was it clear that this would come out from a math or purely math?
Yeah, so we first thought about. I was very interested in this case of K3 times elliptic and programming stuff. And essentially, if you study Gromov-Witten theory of the space, you can use the product formula and just write it as Gromov-Witten theory of K3 surface times Gromov-Witten theory of elliptic curve, viewed as an intersection product in the model space of curves. And that means that somehow, if you want to study modularity in here, dependence on this quasi-modular parameter, you need a better formulation of the holomorphic arm equation than just what was known before. And so something for the elliptic curve, the first case that came was the elliptic curve and formulating in this correct way. And then I was thinking about the K3 surface, how to formulate it for the K3 surface. And then essentially this is what is coming out. So the elliptic curve, in some sense, the way I formulated it is just a special case of the general conjecture, this cycle value theory. If you set up the cycle value theory for elliptic curve, that you can do. And then moving it to the K3 surface essentially requires you to formulate it like this. And it's kind of this thing in mathematics, it's easier to do the general case than to do a special case. So if you just do a special case, you, yeah. In some sense, the general case was, so, yeah. When you assume that there should be a structure for the general case, that prohibits you a lot of paths that you can go, because you cannot go a special path. You can only go a path that is defined for an arbitrary elliptic curvature. And when you think about this, then essentially you have no choice.
And what's the prospect for proving it generally? What do you think?
Yeah, I mean, there's work of Yanda and who have tools. I mean, for example, here, I mean, there's two groups who prove holomorphic arm equation for the quintic threefold. And their methods, in some sense, should also work relatively. So for the quintic threefold case, you X embedded into your P4, and then you made the Gromov-Witten theory of your X to the Gromov-Witten theory of P4 with some fields. And here, of course, you have X that sits inside the projectization of the corresponding bundle here. What is it? Oh, 3 times this section. And so this is a P2 fibration where you can study the Gromov-Witten theory. So you want to do a relative version of the story. The problem with this is that the fibers become singular. And so then it's really a lot of technical work. And so there's some hope, but it's not, I don't know what's this at.
Any question? So then we thank you again and